Okay, in chapter section 16.4, we talk about absolute motion. And with absolute motion, a body subjected to general plane motion experiences both a translation and a rotation. For example, a rolling sphere on a surface where there's no slip occurring will obviously have an angular velocity about the center of gravity and angular acceleration. It'll be in the direction of omega if it's accelerating, and in the opposite direction of omega if it's decelerating, and this produces a velocity of a translation velocity of the center of gravity and of every single point in the body, and acceleration with the same idea. If the body is accelerating to the left, it will be in line with the velocity, otherwise it will be in the opposite direction of the velocity. So at any given instant, the sphere has both a velocity and potentially an acceleration. We can characterize this motion by knowing the following: knowing a angular rotation of a straight line in the body, and to the translation of a point in the body. So say our body moves from here to here. We can characterize the angular rotation. So here's our CG point. Let's just call it G. And then here's the point over here at G prime. So if we think of a point A here touching the ground, as the sphere rolls from G to G prime position, this A will move up to this point in the wheel, and we can sketch out the rotation of this point A. Actually, really, it's not the same point, but as A moves to essentially A prime up here, there'll be a rotation that occurs. Theta. Similarly, we have a translation here, x. And I can relate this x to the arc length here. So x equals this arc length. The distance we travel equals the arc length here of this, which equals r times theta. So if I differentiate that x, I get x dot equals, since r is constant, pull it out, and we only have a theta dot, which of course is our angular rotation. So we could say that our angular rotation equals v over r. And this, of course, can relate to the velocity of the center of gravity, just to generalize. We could take another derivative, so essentially x double dot equals r theta double dot equals r, we should have an r here actually, equals r alpha, the angular acceleration, so alpha equals x double dot over r equals the acceleration of g over r. So let's look at this example. We have a link rotating clockwise here, and at the instance the slotted guide rod is moving to the left with a velocity of 5 meters per second and an acceleration of 2 meters per second squared. So let's find the angular acceleration and velocity of the link AB given these dimensions and this setup. So let me first draw a schematic to help out with this analysis. So we have our link here, AB, and we have the rotation theta, and then in this direction I'm going to define the line of action of our motion. So call that x. So then x, we see here, we can relate x to our angular motion by x equals 0.2 cosine of theta, which means then that the first derivative of x, I jumped already to the second derivative, the first derivative of x is minus 0.2 sine of theta, but theta is also a function of time, so we'll end up with a theta dot. I forgot to give the instant when theta, let's say, equals 60 degrees up here, the slotted guide rod is moving to the left. So we need that in order to solve for theta. So now let's put in our values here. So we have given 5 meters per second velocity here. This is negative because the direction of our velocity is opposite how I plotted my x. And we have minus 0.2 sine of 60 degrees times omega, which we are looking for. One equation, one unknown. We'll be able to solve for omega. Therefore, omega equals 28.9 rads per second. Let's go ahead and box that, since it was one of our. Let's move on to the acceleration. So if we differentiate this again, x double dot equals, so this is 0.2 cosine of theta dot, and then we also have to multiply this by our current theta dot here, and then add to this, since we're doing product rule, add to this minus 0.2 sine of theta times theta double dot. Plugging in our value for omega here, and our value is 60 for theta, we end up with an acceleration of minus 2 meters per second squared. Again, this is in the opposite direction of our positive x. This then equals 0.2 cosine of 60 times 28.9 rads per second squared minus, may as well just go with the minus here, minus 0.2 sine of 60 theta double dot, which I'll just replace this with alpha, our angular acceleration. And we can solve directly for our angular acceleration since it's the only unknown here. And that equals 400 and, well, minus 470 rads. Minus 470 rads per second squared. So essentially that's going to be 470 rads per second squared in this direction, which is opposite theta. Notice that our omega actually is in this direction. So we are accelerating in the opposite direction of our angular velocity.